All right, this is the lesson video for sections 12.3 and 12.4, the dot product and the cross product for multivariable calculus. And what I want to tell you about today is, as you go through this video, this is a lot of calculation that's relatively simple. However, what you're going to find a lot in your assignment is that you're going to have a good conceptual understanding of what's going on when you do a lot of your assignment. So I'm going to show you the basics of this and talk a little bit about what's happening geometrically when we do a dot product or a cross product. But I want you to really be thinking about, as you work through the assignment, try to conceptually think about what are these calculations actually doing. Try to visualize graphically what's actually happening. Okay, so the first section that we have here is the dot product. And you guys have all seen dot product and cross product before. And so this is really going to lead us into the idea of dealing with equations of lines and planes in 3 dimensions. So with the dot product and with the cross product, the calculations themselves are things that you should be familiar with. The way that we apply them will be something that's probably going to be a little bit new. So for the calculations themselves, I didn't put a lot of practice on that in here, or excuse me, in your assignment. That's where I put a lot of the practices in the homework. And then also, like I said before, a lot of that conceptual understanding will show up in the homework as well. So for the dot product, if you think about it, when we went through vector operations in 12.2, we did a lot of things where we were adding vectors, subtracting vectors, multiplying a vector by a scalar, finding the magnitude. But one thing we didn't talk about is, can you multiply 2 vectors together? And there are ways that we can, sort of do vector math to multiply vectors together. And that's really what the dot product and the cross product are. So it's not quite as simple as what you would think when it comes to multiplying vectors together, and what it means is probably a little different than what you might think when you just think about typical multiplication. So what I want to start with here is just this general idea of how do we do a dot product. So if we have 2 vectors here, you can see we have the vectors A and B, and we're just calling the components A1, A2, A3, B1, B2, B3. When I find the dot product, all I have to do is multiply the corresponding components and then add those products together. So notice that I'm getting a scalar result. So I'm getting an actual quantity as a result. Now, that number is what's important. What does that number actually mean? Finding the number is simple. Understanding what the number is actually going to tell us is the important part. Okay, so I'm going to skip down here to theorem 3, because this is really the important part of the dot product. When I find a dot product, notice what it actually means. It means I'm taking the magnitude of vector A times the magnitude of vector B times the cosine of the angle between those 2 vectors. So really the number one use for dot product for us is going to be finding the angle between 2 vectors. Okay, so we'll come back to that in just a second. Now there are some dot product properties that most of these are pretty simple. If you think about what's actually happening when you do these processes, it's pretty simple to understand why these work out the way they do. A lot of these properties are things that you're going to have to go through and show that they are true in your assignment. But you will see as you look through, these first 5 that we have right here, when you look through those and you think about what's the actual numerical operation that's happening here, it makes sense that these properties are what they are. A lot of them are similar to properties that we see just dealing with, numbers like associative property, commutative property, things like that. Okay, so think about those properties on your assignment, and like I said, you'll spend some time understanding why those properties work the way that they do. Now, the common form that we use for the dot product, this is very common for us to use as a setup for dot product, because oftentimes we're using the dot product to find the angle between 2 vectors. And what you'll see is when you find that dot product, it's usually pretty simple to do. And that's what we're going to do on the next problem here. But finding the angle, that's typically going to be something that is going to involve working with a calculator. Okay, so let's take a look at just a really quick, easy example as a reminder of how this works. So this problem says find the dot product between these two vectors. So if I'm going to find the dot product, remember, I'm just going to I'm going to multiply the corresponding components, and each product that I get, I'm going to sum those up, and that's going to give me the dot product. So in this case, for the I components, I have 3 and 2, so 3 times 2. For the J components, I have -2 and 1. And for the K components, I have 1 and -4. And if you add that all up, you can see we have 6 minus 2 minus 4. We get a value of 0. And we'll talk about the significance of that in just a second. But you can probably think about that and think, okay, well, if the cosine of the angle is equal to A dot B over magnitude A, magnitude B, if the cosine of the angle is 0, what does that mean the angle is going to be? Okay, so that's what I want you to be thinking about. And we'll go through, what the general rule for that is in just a minute here when you're thinking about those angles. Okay, so here's one of the properties, and I wanted to show you an example of one of these properties being proven to be true, because you're going to have to do this on your assignment a little bit. So when you have one of these vector properties and you want to show that it actually works, essentially what you're going to do is use just sort of arbitrary vectors, A, B, and C, or A and B, whatever you need, and then you just give the components names that correspond to the name of the vector. So A1, A2, A3, B1, B2, B3, C1, C2, C3, and so on. And then you perform the operation that's described by the property and show that, the two sides of the property are indeed equal. Okay, so here's an example of finding the angle between two vectors. Okay, so when we use the dot product, it's often going to be in situations like this. Okay, so we have vector A, in this case, is 2, 3, -4. And one thing that I need for my dot product is I need to know the magnitude of that vector. Well, we talked about finding the magnitude of vectors in section 12.2. This one would be the square root of 29. So you should know where that comes from. Finding the magnitude of vector B, also something you should know how to do. In this case, that turns out to be 3. That's pretty easy to see. And now if I want the cosine of the angle between them, remember that's equal to the dot product divided by the product of the magnitudes. So the dot product here would be -2 plus 6 minus 8. So where that came from, again, is multiplying these corresponding components. Okay, so I'm going to go through a lot of this pretty quickly because a lot of these calculations are very simple and you've done them before. At this point, I would just use the calculator to solve this out. Obviously, you could simplify this a little bit, but in the end, if I got my answer in radians, it would be about 1.821 radians. Well, most of the time when we use these types of applications, we're going to be doing this in problem-solving situations. And most people's brains don't think in radians. Most people, if I give them a measurement in degrees, they have a pretty good sense for what that is. If I give it to them in radians, they've got to do a little bit of conversion in their head and figure out what that is. So typically, we're going to do answers in this class that are going to be in degrees. So we're going to work in radians. We can convert them to degrees. Now, keep in mind, we did radians almost exclusively for the last couple of years in calculus, at least the last year if you were in BC, 2 years if you took AB and BC. But there are reasons to work in radians when we're dealing with derivatives, primarily because of the definition of derivative. But there are reasons why we would want to also convert answers to degrees. And problem-solving situations are really those reasons. Okay, so the next question, it says, what does it mean if the dot product of two vectors is 0? So if the dot product of two vectors is 0, essentially what I'm saying is the cosine of theta is equal to 0. So the cosine of what angle is equal to 0? Well, that would be pi over 2 or 90 degrees. So if the dot product of two vectors is 0, that means that the vectors are perpendicular. Okay, so we also have rules that apply where if the dot product is positive or if the dot product is negative, we can figure out the angle between two vectors. So think about if you had two vectors that had an acute angle. So if I have an acute angle, that means I'm taking the cosine of something between 0 and pi over 2. Well, that value is going to be positive. So if I get a dot product that is positive, that's going to tell me I have an acute angle between the vectors. If I get a dot product that is negative, that's going to tell me I have an obtuse angle between the two vectors. So we're always going to go less than 180 degrees when we measure those angles out, but you can still have an acute or an obtuse angle when you measure the angle between the two vectors. Okay, so we can also get something that we call direction angles when we are dealing with the dot product. So a lot of times we want to know, and this really will come into play when we're dealing with vectors and we're trying to think of things like force, when we're trying to figure out how much force is acting in a certain direction. These direction angles can be very helpful. So a direction angle is just basically telling me how far am I off of the x-axis from an angle perspective, the y-axis, or the z-axis. And so we use these angles, alpha, beta, and gamma, to identify, how far we are off of those three axes. So you measure, just like always, if you think about how you measure off the x-axis, you measure counterclockwise about the origin. Same thing when you're measuring off of the y or off of the z-axis. Okay, so when you calculate this, this is the type of problem where you might want to do that. Find the direction angles of this vector, 1, 2, 3. So what I want you to do is just pause the video and take a minute and calculate those out, and go ahead and get your answer in degrees as opposed to radians. Okay, and here's the result that you should have gotten on this. You can see that for our angle alpha, you get 74 degrees, beta, it's 58, and then the gamma is 37. Okay, so again, pretty simple to do. All we're doing is getting some magnitudes off of, our vector. You can see these all have the magnitude of vector A involved. So then it's just a matter of which component are we dealing with. And the reason that we're just going with particular components is you can see that when we deal with, like, for example, alpha, well, I is the unit vector in the x direction. So that's just, the first component dot I. That's where the A1 comes from. And when I'm dealing with the second component, well, that would be the second component multiplied to the J, or the third component multiplied to the K. So that's why you see A1, A2, A3 in that setup. All right, so let's talk a little bit about vector projections. When we're doing problem solving, a lot of times vector projections are going to be important for us. And they're important because if you think about it from a force perspective, if I have a force that's acting on an object and I'm trying to figure out what's happening in some particular direction, then I want to know how much force is acting in that particular direction. And so sometimes what I want to do is sort of break my vector into pieces where one of the components points in the direction that I'm interested in. And that's really what a scalar projection or a vector projection does. So we've got a couple of different notations here. And you can see that there's something here called a scalar projection and a vector projection. Obviously, a scalar projection is going to give me a scalar value. That tells me the magnitude of my vector that points in the direction I'm interested in. When I find the vector projection, that actually gives me the components of the piece of the vector that would point in my direction. So if you think about that from like an IJ perspective, if I want to know how much is pointing in the I direction, well, that would be the vector projection of my vector in the direction that I want. Okay, so notice the notation here. So if I'm interested in what direction am I going to point, notice that we have, and I'm going to make this a little bit bigger so we can see this. Notice that we have this A right here as a subscript. So that's telling me the component of vector B that points in the direction of A. So when I look at the scalar projection is that component, that what's the length of the piece that would point in the direction of A. When I look at the vector projection, then I'm looking at the actual vector that would be part of B that would point in the direction of A. Okay, so we're sort of breaking that vector B into components. Okay, so here's just graphically kind of what we're looking at. This is a force. This is a force function here, or a force vector, I should say. We've got it pointing in this direction. And let's say we were trying to figure out, we were trying to move an object in a certain direction. We're trying to move our object in the direction of this axis, in this direction. So what I would be interested in is how much of my force is actually acting in this direction, right? That's what I want to know. And that's what that projection would get me, is I could get an actual vector projection that tells me, okay, I can break my force into one piece of it that's only going in the direction that I'm interested in. How much of the force is acting in that particular direction? Then if I do something like calculate how much work's being done, it becomes a really simple process. Okay, so I've got an example here for you where I want you to just try to find the scalar and the vector projections of the vector B onto vector A, and I gave you two vectors. This is just 2D, so this is pretty easy to do. So just pause the video, take a minute, work those out, and then when you're done, you can come check your answers. Okay, so here's the answer that you should have ended up with, and you can see that for my scalar projection, I just did A dot B over the magnitude of A, and for my vector projection, I used really what I used, I'll show you here. I used this shortcut that we can do, A dot B over magnitude of A squared times vector A. So that's going to give me a scalar in the direction of A. And you can see where that shortcut comes from. I'm essentially doing my scalar projection, which is what I just found here. That's what we had just found, times a unit vector in the direction of vector A. So you could do it this long way. I chose to do it the shortcut way. I typically do it the long way because I don't want to memorize those formulas. But you can see that that's how I came up with the projection of vector B in the direction of vector A. Okay, so let's take a look at the cross product. So for the cross product, this is the one where, if you remember this from pre-calculus, you start to get into a lot with evaluating determinants of matrices. And if you remember that stuff back from Algebra 2, you probably did a little bit of it. You probably did a little bit of this in pre-cal. Evaluating determinants is something that you're going to have to get really good with. And I want you to get to the point where you don't have to write out all the steps to do that. But let's talk a little bit about the cross product and why it's useful to us, and then we'll talk a little bit more about the actual calculation. So when we find a cross product and why it is important to us, when we find the cross product of two vectors, essentially what we were doing, or what we are doing, is we're finding a vector that is normal to the two vectors we're finding the cross product of. So it becomes very, very valuable to us, especially when we're thinking about equations of planes. We can use that to find the equation of a plane. Okay, so the process for this, here it's got it kind of written down as a formula, and I don't want you to remember this as a formula, but this is what was in your book. So yes, you could remember that. That's not something that's easy to remember. I would prefer you understand how to do this with matrices, and that's what we'll talk about here. So when you find your cross product, you're going to find a determinant of a 3x3 matrix. And that's what we're looking at here. This is just a reminder of how it works. So the one thing you have to remember when you find a 3x3 determinant, you break it into smaller 2x2 determinants, but don't forget about this minus here. That's the one thing that people tend to forget. So let me just show you one of these as a reminder of how this works, and then hopefully that will refresh your memory. So this one says find the cross product A cross B, given that vector A is 1, 1, negative 1, and B is 2, 4, 6. So you might think, well, I've only got, kind of 2 rows and 3 columns here if I think about how I'm going to set that up. But when I do this cross product, let me show you how I'm going to go about this process. So my cross product is going to be set up, or excuse me, my determinant is going to be set up like this. So in my first row, I'm going to put I, J, K. So my unit direction vectors. Then my second row is going to be my first vector, vector A, and my second row is going to be vector B. So this would be vector A cross vector B. Okay, so now just like you see above, hopefully you remember this, but if not, for the first piece of this, I'm going to do I times the determinant, and then I'm going to use, like it says up there, B2, B3, C2, C3. Well, for me, that's 1, -1, 4, 6. Then I'm going to do minus J, and then we're going to use the columns that J is not in. So the first and the third, and we'd have 1, 2, -1, 6, and then plus K. And again, the columns that K is not in would be 1, 2, 1, 4. And then we have to find all of those 2 by 2 determinants. And remember, to find a 2 by 2 determinant, all I'm going to do is 1 times 6 minus 4 times -1. So in this case, that's going to give me 10I minus 8J and plus 2K. Okay, so the resulting vector, that is a vector that is now perpendicular to both vector A and vector B. So one of the things that starts to come into play here is something that we call the right-hand rule. And I'm going to go through and talk a little bit more about the right-hand rule when we have class next time. So we'll go through exactly how that works. It's not difficult, and it really helps you understand which direction your cross product or the cross product result should point. So we'll talk a little bit about that. I'm not going to do that on this video, but you can always look at it in the book as well if you're interested between now and when we have class. They've got a little diagram. You might want to Google it and look at a YouTube video of using the right-hand rule, but I'll show you the right-hand rule in class next time if you haven't seen it. Okay, so just like with the cross product, or excuse me, the dot product, we have a bunch of properties for cross products as well. And these are the basic properties. When we are finding the cross product, the vector that we get as a result is orthogonal to both A and B, right? Vector A and vector B. Remember, orthogonal, perpendicular, basically the same thing. Okay, we can also find the angle between two vectors using the cross product. We don't typically do it this way because the dot product is very quick and easy to calculate. The cross product, like we just saw it, evaluating a 3 by 3 determinant, that's a little bit of work. But you do have this relationship. A cross B is magnitude of A times magnitude of B times the sine of theta. And then if we do the cross product of two vectors and we get a result that's 0, that tells you that those two vectors were parallel. Okay, so let's take a look at an example here. Okay, so notice down below, or up above, it says the length of the cross product A cross B is equal to the area of the parallelogram determined by vector A and vector B. So this is one of those things where geometrically you want to understand exactly what's going on. And so essentially what's happening here is if I'm going to find the area of this parallelogram, what I can do is find the magnitude of this cross product, and I'll show you why it is the case here in just a second. So the first thing that I want you to do is I want you to find that area using a cross product. So you're going to solve a 3 by 3 determinant, and then I want you to check your answer, and then we'll talk a little bit about why that is the case. All right, so here's the results that you should have gotten. What you will notice here, that the first thing I want to point out is what work that I showed. And actually, this is my result right here. I want you to notice the work that I showed. So I didn't show a lot of setup here. I did show the vectors that I'm using. And that's the minimum that I'd want you to show. I did show the setup for my cross product, but all that stuff that I showed on the first one with the 2 by 2 determinants and all of that stuff, I don't need to see that every time. I want you to get to the point that you can do that in your head. So this is where I want you to get with it, where you can get to the point where you can do the majority of this in your head and jump from the setup to the cross product's resulting solution. And then for my area, it was the magnitude of that vector. So when we're thinking about why is this the magnitude of the vector, what does this have to do with the area of the parallelogram? Well, if you're thinking about the vectors, when I'm looking at just some vector A and some vector B, so let's say this is vector B and this is vector A. What I'm really trying to do here is create a parallelogram, right? So this is kind of what I'm looking at. Okay, so if I were to find the cross product, remember that the cross product is magnitude A, magnitude B times the sine of theta. Well, if I were to get this distance right here, and I'm calling this theta, well, what that is actually the magnitude of B times the sine of theta. So now think about the length of this from here to here. That's the magnitude of A. The area of a parallelogram is just base times height, right? So what I would be multiplying together is this multiplied to this. That would give me magnitude of A, magnitude of B times the sine of theta, which is another form of the cross product. So don't just blindly remember why these things work. If you remember geometrically why they work, then you don't have to memorize a bunch of formulas. It'll make sense to you when you're trying to think about, okay, why does the cross product give me the area of a parallelogram? Okay, so we've got a couple more things here on cross products. Just like in the first section, I've got a bunch of properties that you're going to be going through when you actually complete your assignment. So a lot of these you're going to show that they're true in the same way that I mentioned in the dot product section. So you create arbitrary vectors for A, A1, A2, A3, for B, B1, B2, B3, and then you can actually go through the process and show that these are true. So I want you to practice with those as you go through the assignment. Some of these will be useful to us, some of them not as useful, but it is interesting to know that we have different ways that we can deal with this because we're sort of doing different calculations than your typical math. So one that's going to be very useful to us is this number 5, this one in particular. And that one is called a triple product. And so that's what we're going to talk about down below here. When we look at a triple product, the scalar of that, if I actually find the magnitude of that triple product, what it is it's actually the, it's going to be the volume of this shape that we're going to call, or that is called a parallelepiped. And so what it is, it's like a 3-dimensional parallelogram. If I look at any of the sides, they're parallelograms, and I have faces that if I look at opposite sides, those parallelograms would have the same areas. So if I find that 3-dimensional shape and find the volume of it, again, it's called a parallelepiped. I can do that with a triple product. I can find the volume of it that way. And this is another one where you can kind of see where the calculation comes from when you look at this geometrically. So I gave you a diagram here that you can look at to understand, okay, if I were going to find the volume of something, I need kind of like, you know, base times width times height. And that's essentially what we're doing here is the same kind of thing. We know how to find the area of a parallelogram. We just looked at that. And then we're just going to multiply that by a 3rd dimension. And then we've got our volume. So that's essentially what's happening here. So you can see this height is being given by B cross C. And that's where our dimensions are coming from when we're thinking about that volume. Okay, so like I said, if you understand geometrically how these things work, it's going to make it a lot easier for you. So try to look at that and kind of think about why does this work the way that it does, as opposed to just blindly remembering formulas. Okay, so what I want you to do on this next problem, it says use the scalar triple product to show that the vectors are coplanar. So when you calculate this, you'll understand what I mean by that. But go ahead and find that scalar triple product and see what you get for it. So you're going to find the triple product, and then you're going to find the magnitude of it. All right, and here is the result of that. So my A dot B cross C, there is my 3x3 determinant. And then I just went through and I found the magnitude of that. When I evaluated the determinant, it gave me a magnitude because notice this time we don't have an IJK. We have 3 actual vectors within our determinant. And so I ended up with a value of 0. And that tells me that these are coplanar and there's not going to be any volume to my parallelepiped bed, because if the vectors are coplanar, they're not going to form that three-dimensional shape. So these geometric ideas are related to the results that you see. And that's really why understanding what's happening geometrically can help you interpret, these calculations that you're actually doing.
Okay, so the last thing that we have in this section, we've got some basic applications, and what you'll notice as we go through this section and really just moving forward in general, most of what we look at in this course in terms of applications are going to be physics applications. And what we're looking at in this particular case is the concept of torque. And when we talk about torque, if I show you this diagram down below, I think it's helpful. So this is something that, even if you haven't seen this in physics before, this is something that everybody has used before in the real world, which is the whole idea of, here if we're trying to tighten a bolt, or, if you were putting a screw in, or something like that, then it's that idea of essentially using a rotational force to move an object in a perpendicular direction. So it's sort of that normal vector that we're looking at there. So we've got our torque vector, but if you notice the R vector that's here, that's our position vector that points out to the point where the force is being applied. And then we have our force vector, and you can see there's an angle between the position vector and the force vector. And if I want to figure out how much torque am I applying, I just take the cross product of those two vectors, and you can think about with the cross product, that's going to give me the vector that points in the direction of where the force is being applied. Okay, so you can see here that when we do this, we've got our position vector cross product with, or crossed with our force vector. And when we do that, we will get an actual torque vector. And if we go through and then find the magnitude of that, we can find the magnitude of the torque. So it's not that difficult to do. The main thing is just understanding, again, geometrically what's happening here in terms of the cross products. If I take the cross product, that's going to give me that normal vector, and that normal vector is going to be my torque vector.